I want to show a little demonstration. I have a piece of tubing here which I've put on the bottom a piece of tissue paper, and it's filled with rice particles from the base here to the top. And if I lift that up, of course the tissue paper here is supporting the load. Then I can do another little experiment here just to tempt fate a little bit more. I take this plunger here and put that in the top, and I press on it and press on it and press on it, and I'm putting quite a big surcharge load on there, but still the tissue paper is holding it stationary. What we see here is that because there's internal friction in there, the friction is transferred from the vertical to the horizontal or lateral by a pressure ratio, and it's a ratio of the normal pressure at the wall divided by the vertical pressure. Typically for a case like this, the ratio is around about 0.4. And when you analyse the mechanics of this and set up the equation and solve it, you end up with this exponential decay function here, in that the exponential term decays very quickly depending on the geometry and so on, but it'll be roughly about 3 bin diameters or 3 tube diameters coming down. The pressure ratio becomes constant. By contrast, I've shown the hydrostatic line. The hydrostatic line starts off tangential to Janssen's curve at the origin, then continues on. So in the case of hydrostatic loading, the more we fill it, the higher we go, the greater it becomes the pressure down at the base. This is not the case with granular materials. The pressure remains constant. So all that tissue paper is feeling is the little bit down the bottom, up to about, normally about 3 bin diameters. So it doesn't really matter how much load I put on the top, the load on the base doesn't change. And that's quite important, because it also has the benefit of showing that in process operations, if you want to have a constant feed rate or flow rate, unlike fluids where it's proportional to the head, the surcharge head or the hydrostatic head, in this case the level can drop quite a long way and the flow rate won't change. You'll notice that I've used the name Silophone. That's my little bit of comic addition, is that the cylinder is normally a silo, and the plunger, which we can move in and out, reminds me of a trombone, so why not call it a Silophone? Thank you for listening or viewing, and we'll see you next time.